just whatever you know currently from S to V. You don't need to change anything. Right? So which means this edge will not be your predecessor. Because if you go from U to V, it's going to be 15 and it's not less than 11. Right? So if you cannot reduce it, just stay with what you know currently. Only if you can reduce it, you try to reduce it. Is that clear? Okay? So this is what you will do in each iteration, starting from the source. Okay? So let's do an example. So remember this. So this is the relaxation condition. So as you do the example, you will understand it. So then we'll come back to pseudo-index analysis. Okay, so next time I'll try to make it white. Okay, so we have a graph here where I have W. So an exam, I'll give you a graph with all these circles for this vertices. Then these are the edge weights. Okay, so to start with, you have, as I said, 0 for the S. Let's say this S is the starting vertex. So I will say what vertex is the starting vertex. If not, just use the lowest alpha as the starting vertex. Okay? So the estimate to everything else is infinity. Okay? So now we want to, in each iteration, among the vertices that we have not yet optimized. What I mean by again optimized, that we have found the shortest path from the source to that vertex or not. To start with, we have not found the shortest path from the source to anything else. The only thing we have found is the shortest path from the source to itself, which is of weight 0. So S, the starting vertex, is the only thing that we have optimized. Right? So again, really to start with, let's say we have not optimize anything. What we'll do is we'll pick the minimum among all these vertex weights. The minimum is 0. So that's when I say I have optimized the path from S to S. Alright? So we have found the optimal path from S to S of weight 0. So using that vertex, you're trying to relax its neighbors. Neighbors means you're trying to see whether you can find the better path to its neighbors. So what does really mean? So you have a path from S to S of weight 0 and you have a neighbor W of weight 3. And the current path weight from S to W is infinity. That's what this really means. So by going through this edge S to W, can you reduce this weight? The answer is yes, because 0, the current weight from S to S is 0 plus this edge weight 3 is 3. And 3 is less than infinity. So, which means I can make this as my predecessor edge and make this edge weight to be 3. Not edge weight, path weight, right? This is my estimate still. It's not the final optimal value you get. We are not sure. We have to go through the iteration and then decide on that. So this is at least an estimate now from S to W. Similarly from S to U, what can you say? 0 plus 4 is less than infinity. So we can make this as 4 and make this edge as your predecessor edge. Similarly from S to V, this is 5 because this edge is 5. 0 to 5. Right? So the other two vertices X and Y have weight infinity. Because actually this is useful to say, right? Because you don't have a path S formed from S to them. Right? So you have optimized what? S. So you have 5 other vertices left over. Right? So we have completed one iteration, picked up S, the minimum among all 0, infinity, 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 did this iteration by exploring its neighbors. So the next iteration, we have to pick another vertex to start with. What vertex you would pick? The minimum among these weights. 3, 4, 5, infinity, infinity. What's the minimum among this? 3. So that's the time you say I have optimized the path from S to W. The 3 corresponds to vertex W, right? So when you pick the minimum weight among all these vertices, which are not yet optimized, we say at that time we have found the optimal path or the best path, shortest path, minimum weight path, any of this from S to W. And we can later prove that why that case. Okay? So right now for the example, when you pick the minimum weight among this, that's when you say we have found the shortest path from S to W. So what does it really mean? You cannot find anything less than 3 from S to W. Look at the graph, whatever the way you lose anything, you cannot find a path from S to W of weight less than 3. So that's the best path, best weight. Okay? So now let's try to relax the neighbors of W, which means trying to see if we can reduce the weight of the path to the neighbors by going through W. So now we are looking at W, S to W, this is of weight 3, and you look at all the neighbors of W. So what are the neighbors of W? You have X, Y, and V. Right? So let's look at each of them. What about X? The edge weight is 5. So, and the current estimate from F to X is what? So what can you do? If you go from W to X and then F to W, it's going to be 3 plus 5, which is 8, and it is less than infinity. So since it is less than infinity, we can really use that W as the predecessor and make this, right, as the predecessor H from W to X. Okay? And what else? Of course, this edge is there. So what are the neighbors there for X, for W? V and Y. So let's try V. You can do it in any order. You can follow the alphabetical order if you want, doesn't matter. So let's try V. What do you have for V? The current estimate is V. Current estimate is what? 5. So we have to look at the latest iteration. So according to the latest iteration, the current estimate is 5. And what's the weight of the edge from W to V? 1. So tell me what can you do at V? 4. If you go from F to W, it is 3, right? And this weight, edge weight from W to V is 1. So the current estimate is 5. So can I reduce it or not? Reduce it to what? 4. 3 plus 1 is 4 less than 5. So which means instead of taking some path from S to V of weight 5, I can go through W and then go to V. Right? So I can make this edge as my predecessor edge. So whatever the edge was predecessor before this edge, you see here, this edge was the predecessor edge. Right? From S to V. I no longer use that edge as my predecessor edge. I'm going to use this edge from W to V as my predecessor edge of weight 1, and this is now the estimate from S to V. So you see that it is possible to reduce the path estimate from 5 you reduce to 4. Right? By going through some neighbors. What about this Y? Currently it is infinity, right? So you can go from W to Y using this edge, right? What is this weight? 3. So can you change this from infinity to something? To what? 6. Because from S to W is 3 and this edge weight from W to Y is 3. So 3 plus 3 is 6, less than infinity. Okay? So I can make this as my predecessor and this is my estimate again. So what you have optimized is W. You have found the best path from, like when you relax the neighbors, that's what you did. You have found the optimal path from S to W and S is also optimized. So we have 4 you will pick? We have 4 more vertices to pick and find visit its neighbors. That's what we are doing in each iteration, right? You pick a vertex that has a minimum weight among the vertices that are not yet optimized, and then visit its neighbors. So which one you pick now? U. Again, there's a tie here, so you can break the tie in alphabetical order. So U before V, so we pick U. So look at U. You have what neighbors for U? Let me draw the other edge too. So you have U, you have S and V. S is already optimized, which means you have found the shortest path from S to S. So the only neighbor you can try is V. Can you do anything for V from U? Because this edge is of weight what? 2. So if you go through U, look at this again. The current path from S to U is of weight 4, and this guy from U to V is of weight 2, and this is of weight 4. So if you go from S to V, the current weight is 4. And if you go to S to U and then U to V, it's going to be 6. Is everyone clear on that? It is 6. Go to S from S to U plus U to V. So it is 4 plus 2 is 6. We don't want to increase this. We want to only reduce it if possible. Right? So that's why we just retain whatever we have as a predecessor for V. So we don't need to include this edge and V or highlight this edge. Just leave it whatever it is before. Okay? So U has only 2 neighbors, S and V, and we check for both of them. So we can say now U is also optimized. Okay? So what else is left?
Y.
V, X and Y, right? So which one you would pick? V, the minimum among 4, 6 and 8. Right? So which one? 4. So that is V. Right? So this is V, you try to relax its neighbors. Of course W is already optimized, so the only neighbor you can, and U is also optimized, the only neighbor you can try is
Y.
and its weight is 3 here. So what can you do about Y?
You can change it to.
You could or you cannot change. You cannot change because if you change it becomes 7 if you want to go through V. Right? So it's good. Y, 4 plus 3. This is the weight of the path from S to V. Always look at the relaxation principle. Right? And if you want to go through this, it's going to become 7. You don't want to increase it. You want to only reduce it. So this stays whatever it is. If this was a 1, what you would have done? If this was a 1, you would have made it 5. And remember the previous path from S to Y was this. Right? So you would no longer use W as the predecessor. You would remove the highlight on this and make this U as V as the predecessor. If this was a 1. And change this to 5. So here, okay? But in this case, this was a 3, so we will stay with whatever was before. Right? So we have optimized this also. So what else needs to be done? Next iteration. There are 2 choices, 6 and 8. So which one you will pick?
6.
So Y. So you pick Y. That means when you pick Y, it means you have found the shortest path from S to Y, which is SWY. Right? So this neighbor is optimized, this neighbor is optimized. The only one you can try is X. And this edge weight is 1. So what can you do? Someone from this side? We're looking at Y and they're trying to see what can you do for X. Huh? The path from X to Y is of weight 6. This edge weight from Y to X is 1. Make it 7, right? Because it is going to be smaller than 8. The correct estimate of the path from S to X is 8, right? And that path was this, S to 8, right? S to X. So you want to check if you can reduce this further. Can you reduce this further? When you say you can reduce from 8 to what? 7. So that's what we're going to do. So we had this guy as the predecessor edge, right? So we are going to remove this highlight on this one and make this as our predecessor and reduce this to 7. Okay, so S, Y, X. So at the end, so which means you have now optimized Y, the only thing left over is X. So all its neighbors are optimized, so X is also optimized. Right? So what you have now found is the shortest path tree from S to everything, every vertex. So put together all the dark edges. Okay? So put together all the dark edges, it's going to be what? W is going to be 3. And then you have for Y, then for X. And then you have this U, and then you have B. So 3, 3, 1, then 1, 4. So these are the edges that are part of the shortest path tree starting from S. Right? So you should be able to do this given any graph. Okay. So I should have picked up this map. This is more white going back. We'll go do this example next time. But remember, let me just settle this and stop. So each time you pick the minimum edge weight, right? Sorry, minimum path weight. So you have an estimate for all these vertices. So you start with, you have 0, infinity, 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 right? And then you have some numbers. And you want to pick the minimum among these, right? So you use what is called a heap. You know heap very well from the previous class, right? So the heap, the root of the heap from the previous chapter is the what? The maximum value, isn't it? Because a heap, what's the property that we saw there? The root or any intermediate node has to be greater than its two children. Right? And I said at that time we called it as a max heap. Max heap means that's what's the property. The intermediate node has to be greater than its two children. Right? Clear? So here we'll use a heap to store all these values, but we'll use what's called a min heap. A min heap means the intermediate node has to be smaller than its two children. So for a min heap, the root will be the one with the lowest value. Right? For a max heap, the root will be the one with the largest value. So when you remove the root, you pick the maximum value among all those numbers. Here the min heap, the root will be the one with the lowest value. And you remove the root, you're picking the one with the lowest value. So in order to implement this, you will store all these numbers in a heap. And every time, in every iteration, you will remove the root. Right? So that will get you the lowest value among these numbers. Okay? Clear?